So just one point that I'll make my screen full screen, and then I cannot see the chat or the Zoom window. So if you have any questions, please switch on your mic and ask. Okay, so this day 2, I will continue with the theme that we kind of had a look at yesterday. Okay, so the yesterday's talk concluded by looking at the logic system that the type system of COP gives you. Okay, so today we start by exploring that a little bit more, and we will again have some hands-on session where we will try to do some actual proofs. Okay. Okay, so just recall, we had this universe of crop, and this universe consists of all mathematical propositions or logical statements that we want to make about the world. Logical statements live inside this universe prop, and you can write it as a colon prop. You can think of prop also as a type in many sense. Yeah, in some sense you can do it. Okay, and recall that if you want to prove A, which is a prop, you have to produce an element X of type A. Okay? And we also saw that predicate over a type T is captured by a function from T to prop. So for each element of capital T, it will give you a different proposition, potentially different proposition. Okay? So that's called that's how predicates are, and they correspond to what in programming world we call as type families. Okay? For each element of T, you have a type family. And finally, if you want to prove for all x px, then the way you do it is you give a dependent function from T in T to P of T. Okay, so for every T in T, you have to give a witness to the fact that P of T is true. So, which means that you have to give an element of P. Okay. So this is what we saw in the last lecture, and this is the logic that we have been using. Okay. Any questions here? Yeah. So let's move on. Okay, so the logic that we just saw is a form of constructive logic in the sense that there is the only way to produce prove A is to produce an element that witnesses A. Okay? And in such a situation, in the classical logic, the negation is kind of an important thing. But here, negation is a derived concept, and what we do is we define the false proposition, and then we define negation as just A implies false, or a function from A to false. Okay, so let's go over this. So print true is the command which shows what true is. Just a point that I want to emphasize: the true that you see with the capital T is not a boolean; it's a prop. Okay, the true with capital T is a prop. Okay. And it is an inductive type which has just one element called TT. Okay. And false is also the false with a capital F is not the Boolean false. Okay. Boolean false is a constructor of the Boolean type. Okay. Similarly, Boolean true is a constructor of the Boolean types. Okay. They are not themselves props or types. Okay. So this is one distinction that we need to make. So the way I can, so the fact that true has a constructor means that I can prove true. I mean, this should be true, right? I mean, in any logic, I should be able to prove the fact true, right? So we model that by an inductive type which has just one constructor called TT, and that the proof of true. And false is an inductive constructor which has inductive type which has no constructor, so there is no way to actually produce a witness for false.
Yeah, proof.
Okay, and with the analogy of implies being captured by function type, not of A is a derived concept, Not of A just means A arrow false. That is, not of A is the function which takes the prop A and produces the prop false. Okay. So prop A, you give me a prop, a witness for A, I will produce false for it. That is what it says. Okay. Got it? Okay. So
regarding the last one, so what will constitute as a proof for A implies false?
You have to give a function which converts elements of type A to false.
Yeah. So, but you know that you can never create the false is an uninhabited type. Yeah. So what will that function do?
So the point is that this function will have to be given a element. See, this function is not going to produce false. This function is only going to produce false if you give me a value of type A. That's the difference.
But I'm just saying that. So what will that function do? I mean, how can, because there are obviously situations where you want to prove A implies false. Yeah.
Yes.
Yeah. So when you want to provide a witness for that, it takes a
value of type A and somehow produces false. That is what it does, and we'll see how it can do that.
Okay. All right.
Okay, but we just go by the idea that so I mean see, the whole point of this thing is that if you produce such a function from A to false, and Cog accepts it, it in some sense says that A cannot be inhabited, right? Because if A is inhabited,
yes,
then I can apply this function and produce an inhabitant of false.
Yeah.
Okay. So the fact that you're giving me this function, see, take the case of identity function on false. You can define the identity function on false. I have not produced an element of type false.
Yeah.
But I do have an identity function on false.
All right, got it.
Right? You can define that. So that's an example of how that function could produce false.
All right.
Okay? But there are more interesting examples. Okay. But just one point here: that true with capital T and false with capital T are different from true with small t and true with small f. False with small f. So the true with capital T is a proposition. Similarly, false is also a prop. It can have elements inside it, but of course it doesn't have. But it is something that can appear on the left side of a colon. Okay. So when you say x colon y, then y has to be a prop or type or whatever. It cannot be some 5 or something. Okay. So 5 is not a type in that sense. So this distinction should be clear, because this is a point of confusion sometimes. So what are the consequences of such a logic? Oops, I have got the print really bad. Okay, so let me just fix this. Just a minute. So okay, so let me just read it out, and don't give much attention to this. There's some latex gocha. So what we can prove is we can prove we can prove A implies not A, but we cannot prove its converse. We cannot prove not A implies it. We'll see why that is the case. Okay? And we can prove the De Morgan's law, except for the law which says that not of A and B implies not A or not B. Okay? And I will give you an intuition why constructively you cannot prove this. Okay? So we'll look into that proof and have an understanding why this is. So I will now again stop my presentation and go over to the Emacs window. I hope my
yeah. Just a minute.
So let's, this is what we did last time. Okay, so let me also disable the component. Okay, so here is true. Yeah, so true is the inductive type. Oh, so it's a constructor is not called TP, but it's called I. Okay, sorry, I'm mistaken.
We can't see
So
the screen.
the true is a inductive prop.
We can't
It
see
has
the
one
screen.
constructor. Is it not visible? Sorry.
No.
Okay.
Yeah. No.
Yeah. Yeah. So true is the inductive type. You can see that in the bottom window. True is the inductive type, which has one constructor I. Okay, so not TT. TT is a constructor of unit, but yeah, it's a singleton type. Okay. Similarly, there is the inductive type false, which is essentially having no elements. Okay. And you have not, which is just prop to prop, and it takes A to false. Okay, so now let's look at the not lemma in this case. So the lemma that you can prove here is A implies not A. Okay, by the way, the tilde is just a fancy notation for not. So I want to prove this that A implies not out. Right? The tactic intuition just disposes it off, but I would want to kind of I would want to go over this proof in some detail just to get you an idea of how constructively this happens. So let's just about this. We don't need to about it. Okay, so this, let's do this lemma proof by hand. So I'm going to prove this again, but this time what I'm going to do is I'm going to do it explicitly by hand. Okay. Now refine is a tactic where I can give a partially filled expression, and it will kind of throw goals corresponding to each of the each of the fill in the blanks in the thing. So I start just a blank. So that just says that okay, my goal is to prove for all a to prop. Okay. So now notice that there is a for all something to something, which means that I am expecting a function. So let me just write it as fun. Let's say a arrow something. Okay. So now what happens? I try to refine it. Then by refining this, what I am saying is that okay, this I have put a blank here. I need to kind of fill it in. And what is the goal that I need to fill? I need to give a function from a to not a. Okay. So I need to give a function from a to not a. So let me just simplify my okay, no, maybe not simplify. So it's a function from a to something. So it has to look like fun a in a something. Okay. So I refine this. So now I need to produce not a. Okay. So let me just unfold this a bit. Because if I unfold not, it tells me what it is. It tells me that I have to produce a function which takes the as first argument a function from a to false and produces false. Okay, so it is a function argument. So it and it has to be like that. So I do a fun of some f, and I finish this off. Now notice what is happening. So I have to give a proof of false. Okay. But of course, I cannot generate a proof of false. But what do I have with me? I have A and I have F. F is not of A. Okay. So not of A, remember, is a function which takes A and produces false. Right? So if I am given F and if I am given A, I can produce that false. So I can just F. Just give one more step. I have to produce an element of type A, and which I have, and that completes my. Okay. So now if you read this proof, it should be clear how I magically managed to prove false. Okay. The point here is that I already have, so I have an element of type A. Okay. So all I'm saying is that if I have an element of type A, and if you have give me a function which converts A to false, which is not of A, then I can produce false, which is equivalent to saying if you give me A, then I can give you a function which converts not A to false, which is equivalent to saying I can produce a proof from A to not A. Does that make sense?
Yeah, but I didn't actually understand this. Fun A implies fun A, small a colon capital A. What does that mean? Fun A implies?
No. That implies you should read it as, so the notation here is fun x
Okay, it's
something.
a function body.
Yeah, it's the body. It's
Okay.
this is in lambda calculus. This is just whatever lambda x dot whatever.
Yeah, the body.
So this is that function that takes x to something, and this something probably has x in it. Okay. That's the notation.
Yeah.
Okay, I'll go over it a little bit. Maybe I can do this proof again, because it's not difficult. It's the intuition tactics will handle it. But the point is, it's good to go over this proof again. So I'll again comment this out. So I will start by kind of saying that I will do a refine of underscore. So then the goal is as it is. Because it say for all A, then I write on A to something. Okay, it's quite natural. Now we are in business. So we have to take A and produce a proof of not A. But not A, recall, is what? A function which takes not A to false.
But why is not a is a value? A is not a value, no? A is a type.
A is a prop. I have to now.
But why are you not having like fun x colon A? That's my first doubt. Why is not fun?
Yeah, that is going to be that fun. So if you look at the proof here, it is fun. I called it A. Other than that, there's no difference. Now it takes an argument A and produces something. That something is not of A. Okay. That something's type should be not of A.
Okay. Yeah.
But not of A may.
Yeah. That part I understand. But what I don't understand is that what is this first part? Fun A, then the function body. That's what I don't understand. Like, what is that syntax? What does that mean? Fun capital A, then this.
So if you look at the refine without this, you are supposed to give a for all A to something, right? Now recall that for all A to something is just a dependent function from A to something.
Okay. That is that fun A. Okay.
That is the fun A part.
All right, got it. Thank you.
Okay. So let me just maybe I can rename it a little bit differently. So then it should be clear what is. Okay. So so for all P, I'm saying for all P in prop. So when I say for all P in prop, I have to have a fun there, right? Because it's a function. It's a dependent function. It's not an ordinary function. It is dependent on that prop that I give. Okay. So in some sense, this is like the polymorphism that you have in Haskell. Okay. Haskell has this parametric polymorphism, but if you explicitly quantify, you have to have a for all A in type, right? So that's what is happening. Does this make sense? Okay. So let's move on here. Okay, so let's complete this. I could have written it explicitly like this.
So you don't write the type of that f because it is inferred.
That you can figure out.
Okay.
Somehow not liking my equal to way. Oh, I need to give public. Oh, lemma, it does not like it. Okay, so this is an alternate proof where I explicitly write the term. So now let's look at the converse of it, which is not how A implies A. This is impossible to prove. Okay, let's try intuition tactic on it, and then you'll see what went wrong. Okay, so when you do an intuition, what it does is it rewrites everything, and finally, what you have with you a function which takes a function from A to false and gives you false, and somehow magically you have to produce A. Okay. Now, since A is kind of fully parametric, there's no way to produce an element of type A. By constructively, you cannot produce this because what you have with you is a function from A arrow false to false. You could have produced A if you had false with you. Okay, you could have so this is possible. So you can have. This you can do. Okay, this is again intuition. Intuition to do this, and it's good to see the proof also. Okay. It is a induction function on false, so we can again write this explicitly if you want. False. So you kind of pattern match on PF false because there is no constructor. You can just do this. Because P the false data type has no constructor. The match, when I do a match, I have to do a case by case analysis of the possibilities of false. Since the possibilities of false are empty, I can just get away with this. So I can prove false. Sorry, if you give me false, I can prove anything. Okay, but the problem here is that I don't have false with me. What I have is a function which will give me false. So at least if I can, so I have to produce A. So either I have to have A, or I have to have a function from A to false. Okay. Or in other words, if I am able to have a if I am able to have A or not A, then I could have proven this. Okay? But I don't have that. That's the law of excluded middle, and that is not an assumption in constructive kind of logic. Okay, so this is something that you don't have in the logic of. Does this make sense?
Yeah.
Okay, so similar to this thing, the De Morgan's law also, there is one law which is not true. We cannot prove that. I mean, I shouldn't say it is not true. I should just say that we don't prove it. Okay, so let's. Okay, so here is another feature of COP which might be interesting. So you can define a section where you can define some variables, and this variable will be common to all the things that you define here. Okay, so if you go out of the section, for example, so notice that this DM and says things about A and B and all these things, right? these A and B are bound here. Okay, but if you come out of this section, you will see the A and B will become parameters of it. Okay, this mechanism is good if you want to kind of, if you have a lot of functions which have the similar kind of arguments in the beginning, so you can use the sectioning mechanism. So it's it kind of simplifies a lot of code. Okay. So let's go over the De Morgan's law again. So let me fix two props A and B. Okay. So the De Morgan law here says that if you give me not A and not B, then I can produce for you not A or B. Okay, so we will again dispose this off with intuition, but let's do it explicitly by hand. And we will do our define thing. Okay, so it says that give me this. Okay, now it's a function, so I write one of H N A and N B. So I have with me HNA and HNB. Okay. So I have with me a proof of not A and not B. So what I can do here at this point is break it up. I can do a destruct of this. So when I destruct this, I have two proofs. I have a proof of not A and I have a proof of not B. Okay. So at this point, so let me just put a commentary here. So if you give me A or if you give me B, I can produce you false. Okay, so I unfold. And what I get is I have to produce A or B to false. I have to give a function which takes A or B and produces false, and it should be clear what is happening. An element of type A or B is a disjoint sum of either A or B. Okay, but in either of these cases, I have an appropriate function which will give me false. Okay, that's what I am going to use. Okay, so I do an intro. Okay, I have this. Okay, now again, you see at this point, I have to produce false. Now, of course, I cannot produce false, but I have things with me. Okay, I have a function which converts A to false. I have a function which converts B to false, and I have one of A or B with me. I do not know which, but I have it. So I can do a destruct here. And then you will see that there are two possibilities. There are two codes. The first one is a possibility where I have a element of type A and I have an element of type not A. So I can produce false from this. I'll use the exact tactic here. And this will dispose of the first case. I go to the next one. I have a B and I have to produce. And this completes. Yeah, so
this is really like natural deduction. Yeah, these proofs look exactly like natural deduction.
Except that in natural deduction you have negation as well, right?
Yeah, but you can eliminate such.
This is what is known as minimal logic, in the sense that it doesn't have, it is close to natural deduction because you are using the fact that if you look at those modus ponens and all those things, they are actually the type typing rule for imply for the function type. So that is the reason why it is uh, it is the same. And beta reduction in lambda calculus is just cut elimination in natural reduction. So that connection is there.
Okay. So I have another question. So when I have negation A and negation B, when you destruct, so I have an object.
So negation, you have a proof of negation A and negation B.
Negation B.
So it is an and of two things, right?
Yeah.
So if you destruct it, I will get both those things.
So what exactly is the operation destruct doing?
Destruct is just a match.
Okay.
It's a case by case analysis on match.
Okay.
So we can see that proof. I'll do a show proof here. You can see that I'm doing a match on this. A match on this and conj of x naught. And that's what we are. Okay.
So what is it? What is it matching? It gets an object.
It's so you can check so you can see print of and. So and is it takes two prop A and B, and it has one constructor called conj, okay, which takes a proof of A and a proof of B and gives you and of A. Okay, this slash is just a funny notation for or a pretty notation for and. That's it. Okay, so it has only one constructor, which is a pairing constructor in some sense.
So is it a tuple? Is it a tuple?
No, it's a tuple. It's a tuple. You can think of it as a tuple. Okay, and similarly we can check the thing of OR.
And for OR, what will be that?
There will be two constructors, either OR introduction on the left or OR introduction on the right. So you can so if you think in terms of natural deduction, see this is the introduction rule for OR, right? There are two introduction rules for OR, and you have one constructor for each of them. Yeah. And if you take and there is one introduction rule, and that's the conj constructor. Okay. So now when you destruct on the so when you come down here, let's look at this one HAV. So here, when you destruct here, right? Here you will see there is a match on HAV, and there are two possibilities. Either I have OR intro of x1, or I have OR intro of, I mean, for some reason this is decided to call it h1 itself. But you see what is happening here. OR intro of a value of type A, or OR intro R of value type B. Okay, and then I have to take this A and produce this thing. So this is what these are the goals that I need to. Okay. Does this make sense?
Yeah.
So let's move on. See, a similar kind of thing will work with the converse of this is true. That is, not of A and B implies not of A or B implies not of A and not of B. The reason again, I can kind of try to give you an intuition. So if I have not of A or B, that means that I have a procedure which will take either A or B and produce for me. You give me whatever. You give me either A or you give me you give me either A or B. I can produce false one. That is what this function does. Okay? So from this, I have to somehow produce a function which takes A and produces B and this, which you can see why it is the case. If I have A, I will just use that to construct. So this maybe we can write it down. We can try to do it as a definition. Yeah, so it is. By the way, I can write it this way, or I can write it as So since it's an and, it will be a conj. Okay, conj of something. Okay, and what is the first something that I need to have? I have to I have to have here a function. I have to have f and g, conj of f and g. Okay. I have f should take a to false and g should take a to false. Okay, and how do I do that? F should take a and produce false. But I don't have a way to produce false. I can produce from A or B. But then or intro, this will give me an element of, it will take A and produce A or B, and then I apply it to P. And similarly here, I can take B and let me call. And this is how the proof works. Okay.
Okay.
Okay. So now you have got a taste of what kind of constructive proofs look like. We can look at the other two De Morgan's law, and again this De Morgan's law should be, again you can work it out. I have a or of not A or not B, so I have either of this, and this is provable. You can think through it, but this is impossible. Okay. Again, let's try to use intuition and see what happens. Okay, so now if you look at the goals, then it will be clear. I have to produce either a function which takes A to false, or I have to give a function which takes B to false. This is one of these things I have to produce. But what do I have with me? I only have a function which takes both A and B and produces false. Only if you give me A and B, I can produce false, right? From that, somehow I have to give a function which just takes A and produces false, which is not, doesn't make sense. Neither is this possible. Okay, so that is the reason why this is impossible to do. This portion of the De Morgan's law is not possible. Just like the not A to A is not possible. So at this point, I want to make one small thing. If you are stuck with, I mean, people think of constructive mathematics as bad mathematics in the sense that certain proofs will be impossible to do. But there are two arguments for it. You can always put it as an axiom. In Coq, you can add an axiom. Okay, you can just say an axiom and then use that to prove your claim. Of course, all the computational content will be gone. An axiom will be unevaluated. Okay. See, the point about other constructions is that they all have computational content in it. Okay. Whereas if I put an axiom, so if I put an axiom which says true, which says something like there exists n such that some silly thing, let me write it. Successor of n is 0. I've said some silly thing. Okay. Now the point here is that I mean I can start working with this, but this will have no computational content. Foo-P cannot be evaluated to anything else. It will just be a blob which the Coq interpreter will just carry around just like that. Okay. So I can add law of excluded middle as a axiom and get classical logic in that sense. But more importantly, there is an interesting kind of connection which says that I can always find an equivalent constructive statement whose truth will imply so if I'm given a classical statement, classical theorem, I can find an equivalent constructive statement which is true. Okay, in the sense that I can prove that and this classical statement is equivalent to it modulo the law of exclusion. So constructive logic actually is more powerful than classical logic in that sense. So we have to be very careful about what we say when we think of constructive logic. So this is some discussion that we can have later on. But the point here is that the logic, underlying logic in COP is constructive. There is nothing wrong about it.
Is constructive same as intuitionistic?
Okay, so the word intuitionistic has a lot of yeah, in some sense, intuitionistic logic has to be constructive in some sense. So
Oh.
I think yes, but I am not so sure because people have used intuitionistic in settings like temporal logic and all those things. I'm not very clear what it means in that setting.
Okay.
Okay, but I think the original word comes from. I think it comes uh, from Gensen himself, I think, intuitionistic and natural deduction and intuitionistic logic and all those things. I think comes from this place. Someone more knowledgeable on logic might want to comment on this.
So actually, intuitionistic logic is a type of constructive logic.
Okay. Okay.
Okay, so that's
So,
logic.
when you say something is an axiom, you the Squawk will assume that there is an object of that type.
Yeah, it will assume that it's an object of this type, but that object does not have any computational content in it. It cannot be evaluated, cannot be simplified any further, etc.
Okay.
Okay. Whereas all these functions, they in some sense have some computational content in it, right? Although they are some props which kind of are thrown off anyway. But I mean, if you extract them, these props will become nothing. But you can consider the corresponding what do you call it, the type world, and they will all have computational content in it. Okay, so that's the point. Okay, so now let's move on back to our presentation. I just want to introduce one more type. So we saw for all. Okay, so the whole point of all these ramblings is that. Okay, so I think my presentation is visible. So excuse me for the typo here. This what I wanted to say is that only not A implies A is provable, not its converse. And similarly, except for this law, not of A and B implies not A or not B. All other De Morgan's laws are true in the constructive version of it. Okay, so what is the other consequence for this? The other consequence is that a similar consequence happens for all and there exist. Okay, so the point here is that for all the proof of for all x px is a dependent function from p to p of t. That's what the proof of for all x px. Okay, so you cannot just say that okay, the proof of there exists x px is just the negation of this. That's not a good way of doing it because that's not constructive. That's not going to help us. Okay, so we have to kind of seriously think of what the there exists proof would look. Okay, so let's kind of think from first principles. Suppose I want to show to you that the claim there exists A, Px is true. What should I? How do I constructively prove it? Okay, I should constructively prove it by giving a potential witness W of A. Okay, and then proving that that witness is indeed witnessing P of W. Okay, so in other words, what is a proof of there exists A Px is a dependent pair. Okay, where the first component is an element of type A. Okay, and the second component is a element of type P of W. P of the first component. Okay, such a thing will witness for me there exists X Px. Does this make sense?
Yeah.
Constructively, this is the only way to do it. If you claim that there exists an X such that Px is true, then first you have to give me that X, and then you have to give me the proof that X indeed satisfies that property. Okay, so that's what the existential quantification is all about. And there is a Coq type called EX. Okay, so you can see that it's a dependent pair. It has one constructor which takes an X and a proof of Px and produces this type. Okay. So this is the type which, by the way, none of these types are inherent to Coq. You can write it. You can write your own standard library where you can name this something else. They are not in any way God given. Okay. The only thing that we have in Coq, which is that we have the calculus of inductive construction, and rest all are kind of built out of. Okay. Any questions here?
What is this EX underscore intro colon? What does that mean?
That is the constructor of this type.
Okay, okay, that's the constructor.
EX is the type. It has two parameters, A type and P, a prop from A to prop, P from A to prop, and it will give me a prop, okay, and equal to, and this is the constructor. X inflow is the constructor. It will take an X and a PX and produces system. Okay, so this is like this is exactly like the conj, right? This is like and. This is essentially like and, but the point is that it's a dependent thing. The first component and something dependent on it. Okay.
And what does this exist mean? Exist.
I think that's a typo on my side. It is EX of the constructor syntax. It is EX of.
EX. Okay. EX Y T Y.
Yeah, this is not exist. This is EX. Okay. Sorry, it's a typo on my side.
Okay.
Okay. So that is how you define the constructor, right? You just give the type.
Yeah.
So this is how existential quantification works.
So this function is again as like a for all, a type starting with for all. Yeah.
It's a constructor. So you should read this as it takes an argument. It takes two arguments. The first argument is an element of A, but the next argument is something that depends on this. So that is why you have a for all here. Otherwise, you would have written A arrow something, right? That's all. That is the only thing. So this is again very confusing because if you are looking at this thing from Haskell, so Haskell has this existential types. Okay.
Yeah.
And this corresponds to that. But the way existential types are dealt there is with starting with a for all, and that is very confusing because why is something starting with for all called the existential? It is existential because of this fact that you can think of it as a proof of an existential fact. Existential part. You should think of it that. Okay. Okay. So let's move on. Any other questions? I will maybe. Okay, next I want to talk about some function data structure, but I think the logic part is kind of done. At least some aspect of it. Yes. Any other question or remarks? Okay, so I'm going to kind of keep this aside. I'm going to now move to some functional programming again. And this time I want to talk about some function data structure. And we will see two styles of doing things, and they are kind of complementary and they have their own advantages and disadvantages. So that's what I'm going to do next. I think we can, if you want, we can do a break at this point. But maybe before a break, I'll demonstrate this existential type. And then
yeah. Typically, if you want to, let's say, prove something, some statement, let's say there is an identity for addition. You showed the proof of 0 is a left identity for addition, right identity for addition.
Yes.
That was easy proof. But if I want to say there is a left identity for addition, then
you have to produce an object of this kind.
So then it falls upon you. The human has to find out that that 0. Yeah.
Yeah. Correct.
Okay. So. So
okay,
we need to have some idea about that. I mean,
yeah,
it will not fall out of.
Yeah, you have to kind of. You have to. You have to kind of. I mean, yeah, it is constructive. So you have to construct all those things. Just a minute, the exist thing, right? It's a notation. So that is a notation for unknown notation. This is unknown. I'm kind of because in the company talk. This is just a notation for x. So it's a notation. This exists x dot p is a notation for this. Don't bother about the details of it, but essentially it is ex. Okay, so we should read this as we should read this exists y p y as ex ex a p. Okay, so this let me just write it again. Unfortunately, I do not know how to turn off the notation. Yeah, so let me show it. In that view, I am going to define a different version of it. And notice that the first one is a type, not a prop. Okay. So you are kind of saying something is true for all elements. There exists an element in A for which this is true. So the A part is a type, not a prop. And this is there's only one constructor. And what does it do? It takes a witness. The W is the witness. And then it has to take P of W and produce it. This is it. Okay. And what they have done is they have added a notation for this, and that is why it looks a bit fun when you print it out. Okay, so I think we will have a small break. We'll come back and we will discuss some functional data. I think there's 1 hour point, right? This is the 1 hour point. Okay. So now let's move on. So what I'm going to do now is to look at some data structure and some kind of I mean the kind of proofs that we did so far. We will not do that kind of proof. We will more try to kind of build into the type things that we need. Uh, like for example, we want to say things like, I will never take the head of an empty list. Some invariants of your program we want to say, and we kind of put in the types in such a way that this won't happen. Okay, so let's move on. Okay, so I mean, list is the favorite example of all such programming, which is non-trivial and uh, it's simple enough, but it's non-trivial. Okay? So the list of A we can define as follows: list of A is either nil, or it's a cons of an element A, and list of A, and the rest of it. Okay, so either you have an empty list, or it is an element A followed by the rest of it. So these are the two constructors that you have on list. Okay. In Coq, you have some notation for it. If you write x double colon xs, then you should read it as cons x xs. So cons x xs is the list whose first element is x, and the rest of the list is xs. And similarly, you have this notation box to mean, I mean bracket to mean nil. So this notation just keep in mind. Okay, so now let's look at two functions which are almost always the first functions that one write when you encounter list. So the first function is it takes the head of the list. So it takes the first element of the list, produces the first element of the list. And tail function is the function which takes the list and produces the rest of the list. Okay. Now these two functions have a problem, because if your list is not a is an empty list, then what happens? You cannot really take a head, right? And what happens if you have such partial functions around in your code is that when you actually run and say the function encounters the empty list and it takes the head of it, then you are in trouble, because it throws up runtime errors, and runtime errors are not things that you want to deal with. So the whole point of type system is to avoid runtime errors and as much as possible. Okay. Okay, so let's try to define such a head function in Coq. So your definition would look something like this: head A xs. Okay, now let me just explain one important point here. If I write something in a curly bracket, this A, so what it means is that this argument is implicit. So when I call head, I don't have to give A, and Coq will fill that in for me. Okay. So I just have to do head xs to get the head of this. So the definition of head.
I didn't understand. What does that mean?
So if I put it in curly bracket, that means that this argument is implicit argument, in the sense that when you actually use head, you don't have to give this argument. Coq will fill that in. It will figure it out and fill it in. Okay.
Yeah, but
so,
head takes the argument xs now.
It takes A and xs of type list of A. So you always have to say which type it is, right? I mean, list of A, right? So that A has to be bound somewhere. So you have to have an argument A.
Okay. Yeah.
Okay. So unlike the case of.
Yeah. Okay. Yeah, it's like a type class. Yeah.
No, not type class. It is an argument. It's an argument. It's a type. So the second argument is list of A, where that A is this A.
Yeah, but it's like a type variable.
It varies over types. Yeah. Okay. It's a type variable, but in Haskell, point is that if you don't free variables are kind of implicitly for all quantified. That is the point.
Yeah.
But here you have to be explicit about it.
Okay.
But the point here is that you can the fact that I have put it in curly bracket, it means that I can call this head without giving A, because the Coq system will figure it out whenever possible. Okay, so the obvious way to do it is that you match on xs, and if it looks like cons x something, then you return x. But if it is nil, what should we give here? Okay. Now in a language like Haskell or Camel, what you can do is you can just ignore this case. Okay, you can ignore this case, and then what happens is that it might show a warning, but when it will compile, and when you run, if you give it a nil element, it will choke. Okay, and Coq cannot do that, because if it allows for such code, then you can kind of potentially prove anything, right? You can give a partial function which gives you the proof of Riemann hypothesis. Okay, so I mean, you don't want such thing to happen. Okay, so such a function cannot be written in Coq. Okay? You can't write this. In fact, as an aside, if I ask you to give me any function of the type for all a list a to a, you cannot write such a function. Not just head, any function with this type. Okay, so this is an idea that is coming from this theorem called free theorem. Okay? So you cannot give me a function which just takes a list of a and produces a for you. There's no such function. Okay, you cannot write it in Coq. I have to be careful here. You cannot prove this fact in Coq, but you can see that there is no way to do this. You cannot write a function which takes for all a list of a to a. You can't do that. Similarly, if I ask you, give me any function of the type for all a arrow a, then you can see that the only function that I can give is identity function. There is no other function I can write. Okay? This has some interesting connotation. I mean, if you can just think through it. See, the only way I can produce a if I'm given an a. Otherwise, I cannot produce a. I cannot just magically cook up a just like that for every a. I can't do that. Okay? The only function that I can write here is the identity. Okay? This is interesting if you think of the types as a specification. Okay, so imagine that usually in programming you have this notion of specification. First you write a specification and then you write the code. Okay, so if I write this specification for you, the code is completely written. I mean, there is no other code you can give me which will be acceptable. Okay, so in that sense it is interesting. Similarly, if I give you this specification, you will not be able to write any code. There is no function which does that. Okay, so you can already see that strong typing means much more than what we see by directly static. Okay, so
how in what sense it is free theorem?
It's a free theorem because this comes from what is known as the parametric theorem of Reynolds. And the term free theorem is due to a paper by Phil Wadler, which he calls it the theorem for free. So the point, the game that you play there is you give a type and you ask a person to write any function of that type. Okay. So the point is that assuming that your programming language does not have these bottoms, or I mean, it doesn't have these infinite loops, then if you write a polymorphic function a to a, there is no way to write it other than identity. For example, there are other forms of identity functions. Like, I mean, you can other forms of such a free theorem functions. For example, you can show that if you have if you take the signature of map, then all it can do is essentially map the function and then take a sublist or some such. So you cannot really do anything more than that. Is what
again identity.
So you get from the point is that from the type of, why is it called a free theorem? Because from the type of the function you know some properties of that function for free. Okay. So suppose I give you f of this type for all a arrow e. The free theorem is that f equal to identity.
Okay.
Okay, so what we wanted is that we wanted to somehow enforce that when I take a head, I only give empty. I don't give empty lists to it. Okay, so how do I do that? One way to do it is through what is known as subset types. Okay, so what is subset type? I have a type A, and I have a prop over A, and this notation bracket x colon a p of x is a subset type of A, where px is true. So true is given in quotes because for us there is no such thing as true. What we care about is that this prop is inhabited. P of X is inhabited. Okay. So you can think of this as the subsets of subset of A which satisfies the property. Okay. Okay, so something like that you can think. Okay. Now the point in this subset type is captured by this SIG inductive type. Okay. If you look at the SIG inductive type, there is no difference between SIG and EX, except for the fact that the SIG AP is a type, EX AP is a prop. There's no other difference. Okay. So it takes for all X in A, P of X and SIG AP. Okay. So this is also a dependent product. It is a dependent pair. The first component is the element A, element in A. And the second component is the proof of P of X for that element, the first element. Okay. So this is exactly like the existential thing, except that it is a type, whereas the other thing is a prop. Okay. So you can think of subset types as just elements of the sig type. Sigma type as it is called. These are called sigma types. Okay, does that make sense?
Why is it called sigma?
Okay, so EXAP is in prop, but SIG AP is in type. Except for that, there's no difference. So someone wanted to ask a question.
Yeah. So why is it called sigma?
The dependent functions were called pi types because it's like a big product.
Okay.
If you think of A as an indexing object, then it's a big product, and sigma is like a sum. That's the sum type, one for each. Okay. So we can define the empty predicate as follows: empty x's if x equal to the nil list. Okay. Recall that this is not a Boolean condition. This is a prop. Okay. And then I can define non-empty list to be x's in list of A such that not of empty x's. Again, notice that because this A has been declared as implicit, I could write it as empty x's. If I had to write, if this bracket was not there, this curly bracket was not there, I will have to write it as empty A x's. Okay, this is a type of non-empty list. Okay, so now the point is that now I can now say that okay, my head should take non-empty list, and so I will demonstrate that through the proof, the interactive proof. Okay. So let's pause here, and I'll move on to the Emacs buffer. Is there any questions? Okay, so let me just move on to the. Okay. Okay, so let's move on. Okay, so I just I'm going to use a list from the standard library instead of writing my own list, but you can see that it's not very difficult. I will also import the list notations so that I get beautiful notation for this. Now I declare empty of this predicate. If I do a check here, yeah. So what does it do? It takes a list of A and gives me a prop. Okay, and the prop is x's is nil. Okay, And you can see a question mark on A here. And that question mark says that A is implicit. So if I just remove this, then you can see that it is for all A in type list of A to go. So I have to give 2 arguments to it. So now, okay, so now what am I going to do? So let's look at the first attempt to prove this. So I'm going to write the head. Okay. So again, A is implicit, LS of type list of A. Okay, then I have to have a proof that LS is empty. LS is not empty. Then I have to write like this and match LS with this part is fine. So when it is empty, what do I do now? Let me do my standard way of doing it as a design. It is not able to figure out that it's a list. So. Okay, so now I have. Okay, so now you see what is happening. At this point, I need to provide an element of type A. I have with me a proof that A is not empty. Okay, that's all I have. And I have LS. Let me do a destruct here. Okay, so I have a proof that not of empty of empty list. Okay, that's the first proof. And the second proof is so this destruction did work. Okay, so it is not very clear again here. How do I actually give this proof? Okay. How do I know that TF is empty in this point, but somehow the Cox match is not able to figure this out. Okay. Again, this is a point where match is not so straightforward when it comes to dependent types. Okay. Because when you do type checking here, you will have to do some kind of unification, and if you are not very careful, you will end up getting a unification which is not possible to do. So COP has a very simple mechanism for doing a match. Okay, so this strategy does not work. Okay, so on the other hand, if I start with a slightly different way, okay, so I take this argument LS, and then I give a function from empty LS to A, not of empty LS to A. So this argument that I had first, which was an argument explicitly named as PF, I push it to this side. So I write it this way. I'll just comment this part out. Okay, so now I'll match LS. Either it is X colon XS, in which case I don't have to worry what the proof is. So now I am supposed to give a function from the proof to A. Okay. So it takes an argument, ignores it, and just gives X. So that part is fine. Now, what about the empty case? Now, remember here I have to provide an element of type A. But how do I provide an element of type A? There is no way to do it. Okay.
Now, one second. X colon X cons XS. Why do you write fun underscore?
Fun underscore is, I mean, if you don't.
What is that fun underscore?
I can just put. I mean, it's an argument that I just ignore. That's it.
Okay.
See, I am supposed to give a function from this empty LS proof to A, right? Because I moved this argument. We call that as opposed to this. I now have HTTP takes a list and gives a function as the result. And the function is from empty LS, not of empty LS to A. Okay.
Not of empty ls, is it a not of empty? Is it a type or what is that? Not of empty.
That's a type. That's a type.
It's a
That's a
type.
prop actually. That's actually a prop.
But earlier you were writing ls colon not empty. Yeah.
Sorry.
Earlier you were writing ls colon not empty. Now you are writing as not empty ls. That way also it will work. Why do you write it as not empty ls? Can you also write like ls colon non-empty?
No, ls is not of, see, ls colon list type just says ls is of type list type.
Okay. All right.
So now this object, think of this as a type.
Okay, non-empty ls. Okay, all right.
Not empty ls. So it's
All
a
right.
proof that ls is not empty.
Okay.
Okay. It's a proof that it is not empty. But what is the proof that it is not empty? It's a proof that if I show that it is equal to nil, then it will give me a false, right?
Okay. Yeah.
So I can.
Yeah. That's correct. Yeah.
This is just and this you can check. Takes a list of to prop, but it's a take a list and give what takes excess and then gives what it takes a proof of x equal to empty and gives false. That is not of yeah, not of x equal to empty. Not of x equal to empty is the x not equal to empty is just x equal to empty to false, a function from x equal to empty. X not equal to empty is same as x equal to empty. Okay, so that's the state. So I want to kind of give a function from m and not of empty ls to a. Okay. So the value that I need to fill in here is of type. The type of the value is not empty ls to a.
Yeah.
Okay. So it should be a function type.
Yeah.
Yeah. So it takes an argument pf, which is a proof that x is not empty. But I don't need to really know this proof. I don't care about the proof. I just give x because my job is. So since I don't care about this, I can just put an underscore.
Yeah. Yes. Yeah.
Okay, so that part is fine. Okay. Now this part is interesting because here I know that it is empty. Okay, and still I have to somehow give a value of type a.
Yeah.
I mean, rather I need to give a function which takes empty of not empty list.
Yeah.
And give a somehow. Okay. So the point then is okay. So then I need to
apply.
use.
Yeah.
No, you can't apply. But let's do it through refine because that makes a lot of sense. Yeah.
Why can't you apply?
You can't apply, right? What are you going to apply? You will get only false. You will get what you have is. Okay, let's do it through refine.
Yes. Yeah.
If you do it through refine, then it will be interesting to see what happens. Let's refine this part. Okay. This part is I am putting as blank. So to begin with, let's put both of them blank, and let's try to define this thing. Okay, so the first code, this is the first code. I need to give a function from, so I have two codes, right? I have to give a function from, why is it not showing the elements actually? I'm not sure why it is not showing those elements. X and this should be shown. But whatever, I mean, this part is easy. So let me just go over here. Okay, so now I have a proof that the empty list is not empty.
Yeah.
Okay? And somehow I have to produce A. But I know that empty list is empty, right? So I have to use that fact. Okay, so let's just before we go here, let's unfold and then do an intro. So I have a function from empty this to false, and I have to produce A. So I can produce false. Why? Because I know that the empty list is empty. Okay. Remember, I can do one more unfold. So I have a function Pf which takes equal to empty equal to empty, a proof of empty equal to empty, and produces false. I have this with me, and somehow I have to produce A. So the idea here is that if I produce false, I can produce anything else, right? So that is what I do. Yeah, I produce false. How do I produce false? I have a function which takes empty equal to empty to false. So I just do that.
But that thing is only proposition for propositions, no? For prop. Here you want an element of
type. So we can do this for any type. Okay. Because of the, I'll tell what is the trickiness involved. So let's apply PF to EQ. Because I know EQ referral is the proof of empty equal to empty. The empty list is equal to. So I didn't have P. Okay, so I have false with me, and how do I produce A? I do a match on the false thing, and since it has no cases, I just finish it off, and then I'm done. The proof is done. Okay, so this is the final. And be slightly more. Okay, so this is the head function which takes a list and a proof that it is not empty and produces the element that I. Okay, and I can write a variant of it for the subset type. So now I take so read this part. LS is of type list of x's which is not empty and produces A. And how do I do that? I do a pattern matching on LS. It is some x's and a proof that this is not empty, and I just call HTTP on that. That's how I get it. Okay. Does this make sense? Yeah. So now this variant of head. So if I check the type of this, notice that what it does. It takes a element of this subset of this subtype. What is that subtype? The subtype of all lists which are not empty, and produces the element of type A. So this makes sense. This is what we actually want. Okay.
Match was also for proofs, huh?
Sorry.
You wrote match PF EQ reference. So that means that proof objects also match can also match proof.
Yeah, the point about match is the following. See, we will come to this prop versus type distinctions sooner or later. You can match on prop as long as the thing that you produce is, I mean, you should not. So if you do a match and you're doing case by case analysis, then each of those each cases you should return only a type, only a prop. You should not return a type, because if you do that, then you will break the uh, point about prop being something computationally irrelevant. Okay, so objects in type are computationally relevant, whereas objects in prop, I mean, or values of types in prop universe are irrelevant for computation. That is the understanding. So when you try to kind of extract the code, all the prop things will be erased. I will show you by extracting this particular code. Okay. So there is some restriction when it comes to matching with prop. Okay. So match X, where X is a prop object. That doesn't make sense. Match X, where X belongs to A and A is a prop. Okay. You can only do so many things. Okay. If you have multiple matches there, they better be all giving values of type A, of type, not prop. Sorry, the other way. If you match on prop, each of the branch should give you a prop. It should not be a type that it gives. On a type, you have no such restriction, essentially. The thing the absurd thing works for type as well. So this will work with A itself, because I didn't actually look at as long as I didn't look at the proof of, I didn't have multiple cases for the falsity, it's okay, this is accepted. Yeah, so this is how one can define the head function with emptiness thing built into it. So now what has happened is, this is a style of programming where I am not actually proving anything. I am just making sure that some invariants are kept track of in the data set. Okay, so this is a different kind of programming. Okay, this is correct by construction. This involves no proofs as such directly. There is another way to do it, and that is the vector types. So the vector types is like this. What I do is I capture so I capture lists of size n for different n, and they have to be a different type. Okay, so for information, let me just also take the type of this here and write it down. Constructions are all similar. Yeah, so the vector has a difference. Okay, so there is a difference. So the way I've written list of A colon type, right? So this A is what is called a parameter. Okay, vector has both a parameter and an index, but this is called an index. Okay, so vector of A is a function from nat to type. That way you can think about it. Okay, so this the A which is the parameter is common to all the constructors, but this n can keep varying. It's called an index, and this is called a parameter. Okay, so now I define it like this: nil is vector of type A with 0 elements. And cons is as follows. It takes an element of type A, and then for all n, it takes a vector of A of length n and produces a vector of A of length such that the type changes. Okay, and I make the arguments implicit here. I make the A argument implicit for nil V, and I make A and n implicit for the constant, so that it behaves just like this. Okay, so I can do this here. Compute on C of 2, on C 5, and that will be a vector of NAT of type 2. A vector of NAT with 2 values. Okay. Now, if I have this type, then I can define an appropriate head version of it. So here, what do? I do head of a vector of length s of n. So here I am saying that head will only take a vector of length s of n. Okay, and there are no and since it is vector of size s of n, I know that it has to be a cons, and I will get it. Okay. Yeah. There's a catch here. There's a monster sitting here, but I will come to that. Okay. So if I do it this way, and I do a check.
Yeah, but here, how did you escape avoiding this nil V?
So I could. I mean, the explanation is that when I say V is vector A S of n.
Okay.
Now notice that nil is of type what? Vector of A 0, and and there is no and it cannot be a vector of A S of n for any n. So the only possibility is cons. That is how it looks like, but there is a monster sitting inside. So I kind of unravel that monster and show it how it works. Okay, but the point about this is that I couldn't have written this function this way in old versions of Conc. Okay, because what I should be actually giving is this. Okay, so now notice what is going on. It takes V of S of n, and then it matches V. So this is a more complicated match. Okay, so the way it works is, so I'll write down the form. Okay. So what is it doing? So what it's doing is it's doing a match. Okay, so just bear with me this extra construct that you have. I want to give something here. Doesn't matter what you do. So whatever it is. And then you have two things. So I have given unit here, so I use two. Okay, so let me try to explain what it is. So ignore for time being these things. So it will have two cases again. Cons V. part is easy. Okay, so this so ignore. So if you notice this part, okay, ignore these this mess here. But look at what happens. If I am when I give a nil, I am giving some object of type some object of type unit. Okay. So these two branches give objects of different types. The first one gives an object of type unit. Okay. It is
What
not
is
giving
unit?
a
What is
unit.
unit?
Unit is a singleton type which has just one element, PT.
Okay.
It's like true, but at the type world. Okay. Okay. So now what is happening here is that this is a dependent function. Okay. What is it? It depending on whether the n is 0 or not. Okay. If I so the other way to write this is I can write something like this. Okay. Oh, so let me write this. That's painful. Okay, so this is a type which depending on whether the first argument is whether the second argument is 0 or not. It will be either unit or a. Okay, that is what is happening. The return value of this match is depending. So if V is a vector of type vec n naught, then depending on whether V naught n naught is 0 or successor, I will give unit or a. So it is in that sense a dependent function. Okay? So because if it is like this, I can give the nil branch to be TT and the const branch to be A. It so happens that I will be calling this only for vector of f of n. So that's how it works. Okay, so this is actually the code that you will have to write in older versions of Coq. Okay, but newer this is a very common pattern. So the newer version of Coq kind of figures this out, and you can get away by writing this simpler looking.
So there is no way of writing such functions in Haskell, yeah?
Yeah, there is no way of writing. Haskell has some level of type kind of programming, type level programming if you use some higher kinds and all those kind of things. So you can do this, but it's not as easy.
Okay.
Okay, so now we will look at these two variants and look at, we'll just extract it out and see what happens. So the HT is the list version of it, and HTV is the vector version of it. And let's just see them in the camel world. So okay, look at the HTP. Okay. So the HTP is for us it was what? It was a function which takes a list and a proof that that list is not empty.
Yeah.
And then produces this thing. That second proof has been erased. Okay. When you extract, it is completely erased because it's a prop.
Yeah.
Okay. So it has been converted into an ordinary function where on the nil it will just do an assert false. Okay. And on cons it will just return the first argument. Okay. And HD is essentially that is also interesting. HD is what? It takes a subtype of the A list. What is the subtype? It's a subtype which consists of the element and its proof. Okay, but the proof being a prop, the sigma type is just the value itself. Okay? So HT is HTP. So you can see that although these proofs and all were floating around in our Cork world, when you extract, all those things are thrown off. And that is the reason why Cork kind of distinguishes between prop and type. Okay, so this is what I wanted to explain in functional data structure. I will kind of conclude here with an example from.
Yeah, I have one question. So does so in Cork, can you make infinite list?
Depends on what you mean by infinite list.
Like for instance, you can just like one dot dot, like in Haskell, yeah.
So
one
you can't.
or
You
x,
can't.
x
You can't. You can't make it. You can define what are known as co-inductive types, and there you can.
Okay.
So inductive types cannot be infinite in that sense.
Okay, because they are not permanent.
I mean, because you it is a well-found. So the point is that whenever you define a data type, like for example, if you try to define something like let's say some or inductive. You a equal to cons goes to such a thing will not work. So let me call this plus C. So, wow, it did that. I am kind of surprised. Something is A arrow code string have to have a benefit. I'm kind of surprised here, sorry. it should not allow this. You have to have a co-inductive. Don't tell me that it's going to. Oh yeah. So when you do a fixed point, this will not work. Okay. So when you try to do a fixed point like this.
Okay.
This won't work. Because it needs to know that something is decreasing. This won't work. But if you define this as co-inductive, then you can do it. But then there are some restriction on how you destruct it. Okay. So there is a dual restriction there. So what you do is you define the co-inductive strings if you want to do an infinite list.
Okay. All right.
And yeah, so that's it. Okay, so I will conclude by just showing another example of what all you can do with dependent types with no proving actually. So recall the red-black tree definition and algorithms.
Yeah.
So the red-black tree is a binary tree with let's not worry about the search part of it, but let's worry about the balanced condition part of it. So it's a tree with nodes being colored either red or black. Okay, so there are two conditions. The two conditions is that, I mean, it's quite.
Red child has to have black children.
So red node
has to have black.
Should have only black children. And the second condition is that all the black depth should be the same, okay, for each child. Right? Now, what I want to do is I want to kind of show you how we can capture this invariant in the data structure itself. Okay. So again, I am using the I don't need it. So tree. Okay. So I'll assume that the empty tree is black in color. In fact, it could be. I mean, yeah. I'll assume that the empty tree is black. So the constructor nil. Okay. It's yeah, so it's a tree A. There are, you see, A is the parameter, and there are two indices. One is the color, and the other is the height, black height. Okay, so tree A0 is the first constructor. Oh, black. Okay, so the first constructor is just the nil constructor, which gives me a tree of black color and has 0 black height. Okay, and the second constructor, so the red constructor, what does it do? Okay, so it has a node, so it takes A array, and then what should it take? It should take two children, which are black children, right? So for all n, 3A black n arrow, 3A black n arrow, it should take these two children, and n is the black height of these two children. So I have enforced that the two children will have the same black height.
Yeah.
And it should produce 3A red color node with the black height not being incremented. Okay, that's the second constructor. And the third constructor is black. Here again, I take an argument A, which is the node value. And then it can take for all n C1, C2 in color.
Yeah.
3A C1 n, 3A C2 n, 3A black. C1 n. This n has type color. Oh, wait. So this is how you define a red-black tree in COP. Now the point here is that you cannot create a red-black tree which violates these any of these rules. Okay, so by encoding these kind of information, you can make data structures correct by construct, and that is the point that I wanted to. Just like vector n incorporates the length, I can incorporate these two invariants into the data. Okay, so I will stop here and we'll continue tomorrow. Any questions? I will push this code right into my repository so you can have a look at it and see if there is something.